Is it possible to join aircraft and spacecraft parts together without the need for drilling holes and using mechanical fasteners? Your daily experience with everyday objects should tell you that other joining techniques are indeed available. Just this morning, I encountered two classes of joining methods. When I went to the fridge to get my morning breakfast, I saw that my son had left me a note on the fridge using a sticky note. Such a note relies on a layer of glue to cause the paper to stick to the surface of whatever object you want it to. This joining technique of using glue, also known as an adhesive, to stick two parts together is called adhesive bonding. We will revisit the topic of adhesive bonding in a later video. I encountered the second class of joining method when commuting to work on one of the most common modes of transportation here in the Netherlands, the bicycle. If you look at the frame of a bicycle, you see that it is an assembly of structural tubes that have been joined together where the ends of the tubes meet. In the case of my bicycle, the joining technique used is known as welding. Let's take a closer look at what welding is and its use in the aerospace industry. Welding is a joining process whereby two or more parts are fused together using a combination of heat and mechanical force. This heat and mechanical force create the driving force for the two materials to flow into one another, which then fuse together once the joint is cooled. Welding processes create visible weld lines where the joining took place. But what are we left with inside these regions? When looking closely at the section of a welded region, different zones in it can be observed: the weld nugget, the heat-affected zone, and the base material. As can be seen from the following section of a weld, it is possible to generally highlight these regions. However, a clear interface between them does not exist. The materials effectively fuse together to form one material, with local regions where the material properties, such as strength, may be affected due to the welding process. The fusing of material in a weld creates a form of integral structure. The distinct separation of parts is eliminated, which can have many benefits for the structural performance of the part. However, one disadvantage to be aware of is the fact that it reduces the damage tolerance of the structure. We can illustrate this by visualizing the joining of a stringer to a skin panel. If we look at the mechanical fastening and even adhesive bonding, we can see that the stiffener and skin remain as distinct and separate parts. Any fatigue cracks that initiate in one part will be confined to grow in that part. However, for an integral or welded structure, there is no barrier for fatigue crack growth between the skin and the stiffener. Another potential disadvantage to consider is the possibility for thermal distortions. Welding requires a heat source which will melt the weld material, allowing it to fill any space between the parts to be joined. As a result, the fusing of the material occurs when the weld region is still very hot. When the joint cools, the weld will then shrink, pulling the parts together and causing potential distortions in the shape of the overall joint. Such distortions can pose a real challenge when trying to assemble hundreds of parts together that all need to precisely fit. Metals are the most common category of material that is welded, although not all metals are suitable for welding. The extreme heat of the welding process can ruin heat treatments and have an unacceptable effect on the material strength. So we have to be careful ensuring that welding is only applied to those materials for which it is suitable for. Here we see a typical arc welding process. What is happening during these processes is that the rod of weld material is acting as an electrode that carries a current. As the electrode is brought near the base material, an electrical arc forms which melts the tip of the electrode, depositing it in a melt pool. As the material is deposited and cools, it forms the weld nugget as the electrode travels along the region to be welded. An inert shielding gas is blown over the electrode during the welding process to help prevent oxidation of the molten material, which could reduce the quality of the weld. Laser beam welding is an alternative method for welding metal parts together. The overall process is quite similar to arc welding, with the exception of the method of heating used. As the name suggests, laser beam welding uses a high-energy laser beam to melt a rod of weld material, that is then deposited in the melt pool of the weld. As the laser beam and filler rod travel along the joint, the material in the melt pool solidifies and cools. As can be seen in the image, the power and intensity of the laser can allow for relatively deep penetration of the melt pool into the base material, allowing for deep welds without the need for creating a notch in the material to be joined. Friction stir welding is another welding technique that is quite different from the previous two. Rather than relying on completely melting the material to fuse the parts together, friction stir welding relies on using friction to heat the materials up until it softens but does not melt, and then mechanically mixing or stirring the softened material together. As melting does not occur, lower temperatures are needed in the welding process, opening up a wider range of weldable metallic materials. The friction and stirring action is provided by a rotating pin tool that plunges into the material being joined. As the tool both moves linearly along the joint and rotates, the speed of the material is faster on the advancing side of the weld compared to the retreating side of the weld. This difference in speed results in a difference in the mixing and thus overall properties on each side of the weld. Metals are not the only material that can be welded. A specific class of composite materials, known as thermoplastic composites, are made of a reinforcing fiber embedded in a thermoplastic resin system. Thermoplastic resins, unlike their thermosetting counterparts, have the ability to melt and solidify, enabling a number of manufacturing options, including welding. Let's take a look at the main welding techniques available to this class of materials. The first welding technique is known as resistance welding. This technique uses a conductive layer, such as a metal mesh, to melt the composite parts, welding them together. Here we can see the metal mesh embedded between the parts to be joined. An electrical current is applied to heat up the mesh, and a force is applied, bringing the parts together. The current is then removed, allowing the mesh to cool and the solidification of the weld to occur. If we look closely at the weld line after solidification, it is clear that the wire mesh used for heating becomes completely embedded within the structure after welding. The second welding technique we will look at is known as induction welding. This technique eliminates the need for embedding a wire mesh heating element by making use of the conductivity of the reinforcing fibers. Not all reinforcing fibers are conductive, so this technique cannot be used for all thermoplastic composites, but it is applicable to one of the more common ones, carbon fibers. Here we see a schematic of the induction welding process. By applying an electrical current to an induction coil, a magnetic field can be induced which will cause heat-generating eddy currents within the carbon fibers inside the composite material. This heat will melt and fuse the thermoplastic resin between the parts, generating the final weld line. The third technique that can be applied is ultrasonic welding. A huge advantage of ultrasonic welding is the speed at which this process occurs. Welding times can be measured in seconds rather than minutes as with the previous two welding methods. Unlike the previous two methods, ultrasonic welding does not rely on electrical currents to generate heat. Instead, thin layer of resin is used as a heat generator. Force is applied to the weld area by a sonotrode, which also subjects the joint to ultrasonic vibrations. These vibrations cause the flexible resin layer to melt as a result of viscoelastic heating and join the two parts together upon cooling. As you can see, there are many processes available for welding. Materials to be joined, cost, and manufacturing constraints can all contribute to what process would be most suitable for a particular application. It may not be the most ideal joining technique for all applications, but it is certainly one to consider in the design of a structural joint.